Okay, starting with 15a, we're going to write the exponential equations in logarithmic form. There's not really any like super good tricks. You just kind of have to remember the general form. So the general form, if we have b to some a equals c, is that we're going to have log base b of c equals a. So your exponent is always what comes over here, your base always goes right here, and then the number that you're equal to is what goes inside of this logarithm. So going through these questions here following this form, we say we have log base 2, and our exponent is 4, and 16 is what goes inside of our log. So we have log base 2 of 16 equals our exponent. Okay. Next one, we have same thing. We have log, and then we write our base. Our base is 1/2. We write what it's equal to, it's 32. Then we say what's our exponent? Well, -5. Last one, C. We have log, our base is A, we equal B, and then this whole thing is equal to our exponent, which is 9. It's pretty easy. It's just the same thing where your base goes in front and then your exponent goes on the opposite side. Alright, starting with 16a, we're going to evaluate the following logs without a calculator, show our work. So the first thing I'm going to do is take this log and rewrite it in the exponential form, because that's a little bit easier to think about. So we're saying our base is 2. We have some exponent, let's say a, it's going to equal 64. So how many times do we multiply 2 to get to 64? So we have 2 times 2, that's 4, times 2, it's 8, times 2 is 16, times 2 is 32, times 2 equals 64. So now we just add up these. We have 1, 2, 3, 4, 5, 6. So that means 2 to the 6th power is equal to 64, or that log base 2 of 64 is equal to 6. Then we can go through and do the same thing with the next one. So we have 3 to some exponent, let's call it a, is equal to 1/9. So the first thing that we need to notice is that this is a fraction that is less than our original one, which means that this is probably going to be negative. So if we write it as, if we imagine doing something like 1/3 to the a, so now we've just like rewritten it as like a negative a, because if you have a negative in your exponent, that just flips it, or you take like the reciprocal of it. So now here, we can see that this 9 is just 3 squared. So that means that our original a up here, a is equal to -2. So that would bring this down to the denominator, and then we'd square it and we'd get 1/9. Or in this case, log base 3 of 1/9 is just equal to -2. And then last one, C, we have log of 10,000. So notice it doesn't say what the base is, but if you ever see log with no base, what that means is that that's base 10. So log of some number is the same thing as saying log base 10 of that number. So now we just need to know how many 10s do we have to get to 10,000. Well, we can just really count up the number of zeros. So this would be times 10 times 100, which is 10 squared, times 1,000, 10 cubed, and so on. So for this one here, because we have 4 zeros, it's like taking 10 and multiplying it 4 times. So log base 10 of 10,000 is just going to be equal to 4. Okay, for 17, we should have a bunch of expressions we need to simplify. So if we ever have 2 to some exponent where we take log of that same base, they sort of like cancel each other out. So if we just kind of like imagine like crossing out that, all we're left with is the x minus y. So this expression here is just going to be equal to x minus y. Again, if you just have 2 to some exponent of log of that same base, they cancel each other out. So next one, we have a similar situation. We're taking log base 7 of 7 to the 13th. Well, we know by definition what that's equal to is just going to be the exponent of whatever this is to the 7th base. And fortunately, it's already in 7th base. So we know the answer is just going to be 13. So, and again, if you see a base, and this is the same base, your answer is just going to be whatever that exponent is there. So, next one here, we have natural log e x squared plus 2. So, again, this is just like b, except for we have natural log. So natural log is the same thing as saying log base e. So you're basically saying log base e of e to the x squared plus 2. The log base e and e, they sort of cancel each other out, kind of how like they do here, where we're taking e, or in this case, like 7, and then the exponent is all that's left. So this one here is just going to equal x squared plus 2. Okay. Next one, d, we have log base p of p. If it's ever to the same base, we know that this exponent here is kind of like 1. So this one here, we just imagine it equaling our exponent, which is just going to be 1. And then last one, e, we have natural log of e, or excuse me, natural log of 1. So if you have natural log of 1, this is like saying e to what power equals 1. Well, the only thing that gets you the only exponent that'll get you equal to 1 is always going to be 0. So anytime you take the log or natural log of 1, it's just always going to be 0. Okay, 18, we're going to be applying some transformations to this parent function, where this is our parent function here to the graph of the related function this. So see, this is sort of like the quote like inside part. So this number here is responsible for like the horizontal shifting, and then this part here is responsible for the vertical shifting. So what we have here, and again, it's just like with whenever we would have like parentheses x plus 5 squared, whenever we had something like that, even though this was plus 5, what that does is it shifts it to the left 5. And then the one on the outside is just sort of like the normal way you would think. So this one here, we go left 5 spaces, or 5 units, then we go down 2. Okay, starting with 19a, we're going to apply product, quotient, and power properties of logarithms and simplify if possible. So where these properties actually come from is sort of if you were to rewrite them in the exponential form, some of that arrangement that you can do, we sort of like take that arrangement and apply it to logarithms. So in the case of this one here, what we have is log base 4 of root to the 7th, x to the 5th. So the first thing is I'm going to notice that we can rewrite this as x to the 5/7. So if you have the square root, it's like saying 1 over whatever power that root is. So then, using powers of logarithms, we can just take this exponent here and bring it out front here and say that this here will be equal to 5/7 times log base 4 of x. Okay, for b, we have log with no base, which means that it's base 10, of m squared plus n over 100. So first thing is we can apply a quotient rule and say that this here is the same thing as if we had log base m squared plus n minus log of base 100. So if you have a fraction inside of a log, you can always split it apart like that, where your denominator is a minus. And you can do the same thing where if you have two things multiplying, except for you can separate them with a plus in between them. So the next thing is that this log base 10 of 100 is just going to be 2, which means that this whole thing altogether is going to be log base 10 of m squared plus n minus 2. And we can't do anything with this m squared because there's this plus n here. If it was just log of m squared, then we could do something with it, but because we have these two together, and they're not like, if it was like m plus n all squared, then we could pull it out, but because it's not, we can't really do anything else with that. Okay, and then c, we have log base 7 of 49k. So first thing is if we have two numbers that are multiplying in here, we can break those apart to be log base 7 of 49 plus log base 7 of k. So then we know log base 7 of 49. So if you add 7 to what exponent equals 49, that's just going to be 2, which means that we can rewrite this all as 2 plus log base 7 of k. Okay, 20, we are going to write the logarithm as a sum or difference of logarithms and simplify each term and show our work. So we have natural log, which again is log base e, of the fourth root of x squared plus 4 over e cubed. So the first thing I'm going to do is remember that if we have anything to like a root like this, we can rewrite it similar to this, where we have x squared plus 4 over e to the third, all to the 1/4 power. Then we can use the power property to bring this 1/4 out front. So now we have 1/4 times the natural log of x squared plus 4 over e cubed. Here, okay. And then from here, because we have two that are to like a fraction here, we have this x squared plus 4 in our numerator and e cubed in our denominator. We can break those up into two separate logarithms. And we also have to know that they're both technically attached to this 1/4. So we're going to have 1/4 natural log x squared plus 4, and then minus 1/4 natural log of e cubed. So next, what is the natural log of e cubed? So the 1/4 natural log of e cubed. Well, if we had log base e of e to the third, that's just going to equal 3. So this here is the same thing as saying 3 to the 4th power, because we sort of like cancel out this e and we just look at this exponent here. So if we were to rewrite all this from here, and there's no other simplification that we can do from here, our original logarithm simplifies down to 1/4 natural log of x squared plus 4, and then minus 3/4. Okay, so for 21, write the logarithm expression as a single logarithm with coefficient 1. So what this one is doing is basically the exact like reverse of 20. So if we have 4 log base 6 of r minus 3 log base 6 of s minus 2 log base 6 of t. First thing I'm going to do is take all these coefficients and take them and put them up here with our exponent. So we have log of r to the 4th plus log base, oh, these are base 6, sorry, of s to the negative 3 power plus log base 6 of t to the negative 2 power. Now if I have two logs that are adding, or three logs that are adding, I just get to take all of them and put them in the same log as multiplication. So from here, I have log base 6 of r to the 4th, s to the negative 3rd, t to the negative 2nd. And the last thing that I'm going to do, excuse me, is because these are negative exponents, I'm going to bring them down to the denominator and make them positive, which means that our answer is just going to be log base 6 r to the 4th divided by s to the 3rd, t to the 2nd. Okay, for 22, starting with A, so the variable pH in the formula pH equals negative log H plus represents the level of acidity or alkalinity of a liquid, and H is the concentration of hydronium ions in the solution. This is a really common thing in chemistry, and it's just like how acidic or basic things are. So starting with the first one here, we have a tomato with a concentration of H of 6.31 times 10 to the negative 5th moles per liter. We're going to find the pH. So all that we have to do is follow our equation here, that pH equals negative log base 10 of the hydronium ions. So from here, all we have to do is just plug 6.31 times 10 to the negative fifth and enter that into our calculator. And if we type this in as, we would have negative log base 10 of 6.31 times 10 to the negative fifth. If we enter this into our calculator, we will get roughly, if we round to one decimal place, we'll get 4.2. And 4.2, this is just going to be a unitless measurement, I believe, of just like how acidic it is. Okay, so we're just going to be continuing on from before, where we had pH equals negative log base 10 of your H. So if we know H for milk of magnesia is 3.16 times 10 to the negative 11th, our pH is going to equal negative log base 10 of 3.16 times 10 to the negative 11th. So if we enter this into our calculator, we should get that the pH is 10.5. This is going to be unitless, and 10.5 is pretty like basic. I believe it's like 7 and above is considered basic, and 7 and below is considered acidic, which is more so something that you would really only worry about in chemistry. But for this next one here, for B, this time we're going to be doing the opposite, where we're going to determine the H of each one and round the 2 decimal places. So if pH equals negative log of H, how can we go ahead and solve for H here? First thing is we move the negative to the opposite side of H. And then to undo this logarithm, we take everything to the power, or 10 to the power of it. So we kind of write it like this. So we get that H is going to equal 10 to the negative pH. So for an onion with a pH of 5.6, the concentration of the hydronium ions is going to be 10 to the negative 5.6 power. And if we enter this in, we should get that our concentration is 2.51 times 10 to the negative 6th. And this time we do get units, and our units are going to be moles per liter. Okay. Then for the next one, we have baking soda with a pH of 8.4. So H is going to equal 10 to the negative 8.4. Then if we go ahead and type this into our calculator, we should find out that the H is going to be 3.98 times 10 to the negative 9th, and our units again are moles per liter. Okay, for 23, given that log base B of 2 is approximately 0.356, and that log base B of 3 is approximately 0.565. Approximate the value of log B of 24, show all work. So what we need to do here is sort of figure out how we can take these two logarithms here and combine them in a way to get to this. So first of all, the one thing that I'm going to do is think of some factors of 24. So 24 can be broken down into factors such as 2 and 12, 3 and 8, 4 and 6, then there's also 1 and 24. So ideally, I'm going to be able to take these two and get them into some factors like this. So the way that I'm going to set this up is I'm going to say that we're going to have x times log base b of 2 plus y log base b of 3. What we want to get is log base b of 24. So the next thing is that I'm going to have combine these here to where I get log base 2 to the x plus log base b of 3 to the y. So then because these are adding, I can bring them in together to the same log. So that way we have log base b 2 to the x and then 3 to some y. So from here, this is kind of one of the parts where we have to do a little bit of thinking here. So we know that we need to find a way for x and y to get us to one of these factors here. So the easiest one is that we can have 3 times 8, because that would mean that y would equal 1, and then x would equal 3. And in that case, we would get, this would be 2 to the third is 8 times 3, which is 24. So because of that, we can go ahead and say that x will equal, in our case, 3, and y will equal 1. And there's probably a bunch of different ways that you can do this, but these are sort of like the easy factors that we can break it apart to. And we want to just stick to the easiest things that we can. So from here, I'm going to take this and plug it back in up to here, because I know what log base b of 2 is, and I know what log base b of 3 is, which means that log base b of 24 should equal 3 times our approximation, which was 0.356 plus 1 times our approximation of log base b of 3, which is 0.565, should equal log base b of 24. So now if we plug this into our calculator here, 3 times 0.356 plus 1 times 0.565, we should end up getting that log base b of 24 should approximately equal 1.633. Okay, 24, use the change of base formula to evaluate log base 6 of 23 using base 10 or base e. Show all work. So your change of base formula is just, it's really useful because a lot of calculators might not have the ability to evaluate log base 6 like that, but we still want to be able to enter it into our calculator in a way that it can solve it. So let's say we had log base b of a. This is the same thing as if we had log base 10 of a divided by log base 10 of b, or we could also use it using natural logs. So in this case here, we have log base 6 of 23, which should be the same thing as evaluating log base 10 of 23 divided by log base 10 of 6. Or again, we could do it using natural logs by saying natural log of 23 divided by natural log of 6. So now if we go ahead and enter these into our calculator, I'm just going to use the natural log one. So natural log of 23 came out to be 3.135, and then natural log of 6 came out to be 1.792. So now if I take these two and I divide them, I get that log base 6 of 23 should equal roughly 1.75. And if your calculator is able to enter log base 6 of 23, you'd get that same result as if we just entered it using one of these two methods here.
Okay, now to look at question 25. Solve the following exponential equations. Give an exact solution in terms of common logarithms or natural logarithms and an approximation to 4 decimal places as needed. Show all work. Let's start with a here. So we have 5 to the power of 3x minus 2 is equal to 625. So one thing is we want to get that power before it's not a power anymore. So one thing we do is take a natural log of both sides, and using our log rules, we know that that's going to come down to out front. Right? So we know that our power is now out front, so we have that 3x minus 2 is equal to natural log of 5 is equal to natural log of 625. Sorry, 3x minus 2, all that times natural log of 5. Putting your parentheses here is very important to make sure, because this natural log of 5 term is getting distributed to the 3x and the negative 2. Right? So now we're going to have a 3x natural log of 5 minus 2 natural log of 5 is equal to natural log of 625. Now we get our like terms together, so we're going to leave our x's on the left side, so natural log of 5. Now we're going to add 2 natural log 5 on both sides. Now we're going to have natural log 625 plus 2 natural log of 5. And then now we want to get the x all by itself. We want to know what x is equal to. So we're going to divide both sides by 3 natural log 5. So then we know that x is going to be equal to natural log of 625 plus 2 natural log 5 all over 3 natural log 5. And this is going to be our one of our exact solutions. But when we simplify this, put it in the calculator, we also get x is equal to 2, which is an exact solution and our approximation at the same time. Next, we'll look at part B. We want to know 6 to the power of 2x minus 5. Let me write that a little better. 2x minus 5 is our power, and then minus 8 is equal to 12. So I'll go ahead and move over this 8. So we have 6 to the 2x minus 5 is equal to 20. So what I want to do is take a log or natural log of both sides so we can get that power out front. So I'm going to do a natural log of both sides. So we're going to have 2x minus 5 times natural log of 6. Those parentheses are very important because that natural log of 6 is going to get distributed to both terms here in a second, which is equal to natural log of 20. So we're going to distribute that natural log of 6 to the 2x and the negative 5. So we're going to have 2x natural log 6 minus 5 natural log 6 is equal to natural log of 20. Next, we're going to add the 5 natural log of 6 onto both sides. So we're going to be left with 2x natural log of 6 is equal to natural log of 20 plus 5 natural log of 6. So next we want to get what x is equal to. So we're going to divide both sides by 2 natural log of 6. 2 natural log of 6. So we know that our exact answer is going to be natural log of 20 plus 5 natural log of 6 all over 2 natural log 6. Another way we could write this is just using any type of log. So we could also write it as log 20 plus 5 log 6 all over 2 log 6. And putting this in our calculator, we know that we're going to get an approximate solution of 3.3360. So next we're going to look at part C. Part C has 4 to the power of x plus 2 is equal to 6 to the power of 3x minus 4. Like we've been doing, we want to take the natural log of both sides so we can bring our exponents out front. Remember, it's very important to keep our x plus 2 in parentheses. 4 is equal to 3x minus 4. Very important to keep that in parentheses. Natural log of 6. So our next step, and why it's important to keep it in parentheses, is so we can distribute this term. We're also going to distribute this natural log of 6 to both sides. So we're going to have x natural log 4 plus 2 natural log 4 is equal to 3x natural log 6 minus 4 natural log 6. So we want to get like terms together on one side. So I'm going to move this x natural log 4. I'm going to subtract it on both sides. X natural log 4. So we're going to be left with 2 natural log 4 is equal to 3x natural log 6 minus x natural log of 4 minus 4 natural log 6. Right? Well, we'll keep x's on our right side, so we're going to add that 4 natural log 6 onto both sides. So we're going to have 2 natural log of 4 plus 4 natural log of 6 is equal to 3x natural log 6 minus x natural log of 4. So on our right side, we're going to want to factor out our x. So we have x by itself. So 2 natural log 4 plus 4 natural log of 6 is equal to x times 3 natural log 6. 3 natural log 6 minus natural log of 4. So now to find what x is equal to, we're going to divide both sides by 3 natural log 6 minus natural log 4. 3 natural log 6 minus natural log 4. So you're going to have x is equal to 2 natural log 4 plus 4 natural log of 6 all over 3 natural log of 6 minus natural log of 4. Right. So now when we plug this into our calculator, we're going to have x is approximately 2.4918. So we can go back up here. Another way we can write this term is 2 log 4 plus 4 log 6 all over 3 log 6 minus log 4. And this is also equivalent to negative 4 log 6 minus 2 log 4 all over log 4 minus 3 log 6. Now looking at part D, we're given e to the 2x plus 2e to the x minus 24 is equal to 0. So one thing we want to recognize here is this kind of looks like a quadratic, so we're going to make a substitution. So we're going to say that u is equal to e to the x. So we're going to say u to the 2 plus 2u minus 24 is equal to 0. Now we have a quadratic equation. So there's multiple ways we could solve this. We could recognize what our factors are, or we could use a quadratic equation. So if we want to just recognize our factors, we need to know what's going to multiply to give us negative 24, but add up to give us 2. So what two numbers can multiply to give us 24? We have 6 and 4, right? So one of them needs to be negative, since that's a negative number, and one needs to be positive. Since this 2 is a positive, we want to learn our larger number also needs to be positive. So we're going to have u plus 6, then u minus 4 as our factors, right? So now we know that we're going to plug e of x back in for u. So you know that e to the power of x plus 6 and then times e to the x minus 4 is equal to 0. So now you want to test each one and find out what our x values are. So we can say that e to the x plus 6 is equal to 0 and e to the x minus 4 is equal to 0. So let's start with our left side. So we want to say that e to the x is equal to negative 6. And we want to have our what x is equal to. So we're taking a natural log of both sides. Natural log cancels out our e. So we're left with x is equal to natural log of negative 6. You cannot take negatives inside of your natural log. So this is an undefined solution. Or it's actually not a solution since it's undefined. So not a solution. So next we want to do the e to the x minus 4. So we're going to say e to the x is equal to 4. Take a natural log of both sides. Natural log cancels out with e. So we're left with x is equal to natural log of 4, which it's positive, so that 4 is positive, so it is going to be a solution. So we want to find our approximation, which is going to be 1.3863.
Okay, so I'm going to be working on 26, starting with A. We have log base 3 of 2x plus 5 equals log base 3 of 5x minus 3. So whenever we have two logs on both sides and they have the same base, really we're kind of able to sort of neglect the log and just focus on what's on the inside and making the insides match because they have the same base. So we can just go ahead and write this as 2x plus 5 equals 5x minus 13. Then from here, if we move things around, we get 18 equals 3x, so x would equal 6. So no need to get decimals or anything for that. So B, we have log base 6 of 7x minus 2 equals 1 plus log base 6 of x plus 5. Log base 6 of 7x minus 2 equals 1 plus log base 6 of x plus 5. So in order to get this kind of like here on this last one, we had two logs on both sides. We were able to just compare the insides of it. I'm going to go through a similar process here to where I can try and bring this 1 inside of this logarithm. So that way I just have one logarithm on both sides. So to do that, I'm going to write 1 as a log with base 6. So if we think log base 6 to the 6th, or log base 6 of 6, we think our exponent here is 1, which would evaluate to this. So these two here are the exact same, plus log base 6 of x plus 5. So now if we have two logs that are adding and they have the same base, it's like as if though they're multiplying the inside components. So we're able to combine those two. So we have log base 6, 7x minus 2 equals log base 6 of 6 times x plus 5. So from here, because we have two logs with the same base, just like how we did in A, we're able to just focus on the inside part. So we have 7x minus 2 equals, then if we distribute the 6, we have 6x plus 30. So then next we get everything to all our x's to one side. So we get x equals, and then 32 on the opposite side. Okay, last one. C. Log base 2 of x equals 4 minus log base 2 of x minus 6. So we're going to do the same thing that we did before, where we want to try and bring this 4 here inside. So we're going to write log base 2 of x equals log base 2 of, so now what would go right here in order to get that exponent? It's going to be 2 to the 4th power. So 2 to the 4th power is 2 times 2, which is 4, times 2 is 8, times 2 is 16. So log base 2 of 16 equals 4. So these here are the same thing. Log base 2 of x minus 6. So now we can go ahead and combine these logs. So we have log base 2 of x equals 16, or excuse me, log base 2 of 16 over x minus 6, again, because this is negative here. So next we kind of neglect our logs because they have the same base, and we just focus on what's left inside. And we get x equals 16 over x minus 6. So now we multiply x minus 6 to both sides. We get x squared minus 6x equals 16, or x squared minus 6x minus 16 equals 0. So now if we think of two numbers that multiply to negative 16 and add to negative 8, we can do x minus 8 times x plus 2. What we get here is that x equals 8 or x equals negative 2. But before we do this, anytime that we solve a lot of these log or exponential equations, it's a good idea to always just take your answer and plug it in to make sure. Because sometimes whenever we do some of these operations, we end up getting like undefined answers. And particularly right here, we have this negative 2. If we were to plug negative 2 in right here, this would be an undefined answer, which means that we can't really say that x equals negative 2 because that's just log base 2 of negative 2 is not real. So x equals 8 is really our only answer here for this one. Okay, 27, starting with a. We have a equals p times 1 plus r over n to the nt. And we're going to solve this equation for t, and this is your interest formula. So the first thing that I want to do is I need to figure out a way to get this t out of the exponent. Well, we're going to end up doing that with logs. And the first thing that I want to do is get everything that doesn't have a power of t to the opposite side. So I'm going to have a divided by p is equal to 1 plus r over n to the nt. Next, I'm going to take the log of both sides. Or you can take the natural log. It just needs to be the same base, and you need to be consistent with how you do it. So for this one, I'm going to use the natural log. So if I take the natural log of both sides, we get something like this, 1 plus r over n to the nt. And now using our log rules, we can take this and pull it out front. So we have natural log a over p equals nt times the natural log of 1 plus r over n. So now I want to get everything without a t to the opposite side. So I just divide all of this out. So I get that t equals natural log a over p divided by, we divided by n times the natural log of 1 plus r over n. So this is our final answer. And again, it wouldn't matter whether or not you use natural log or log base 10. It'll be the same thing. You just need to make sure that you're consistent. Okay, B, we have log base 10 of B minus 1.7 equals 2.3 m, 0.3. And we're solving for this equation for B. So my first step is that I want to get everything with B on one side. So I'm going to add 1.7 to the opposite. So I have log base 10 of B equals 2.3 m plus 1.7. So now, how do I get B out of this logarithm? Well, I kind of have to, our step to undo a logarithm is we take it to the 10th, or whatever your base power is. So here, we're to undo a log base 10, you take everything to the power of 10. So this here cancels out, and then we're left with B equals 10 to the power of 2.3 m plus 1.7.
Okay, so for number 28, we are going to use this formula we have in this previous problem in A. So we're going to say A equals P times 1 plus R over N to the NT, right? And so our A in this case is going to be that 800,000. Our P is going to be our 120,000. 1 plus our R, which is our 4.5%, changing to decimal, it's going to be 0.045 over our N is the number of times it's compounded in a year, so that's going to be 12 because it's compounded monthly, times 12, or to the power of 12t. Okay, so solving for t in this equation, we're going to divide by 120,000, divide by 120,000, right? And so then we have, that simplified is going to be 20 over 3 is equal to 1 plus 0.045 over 12 to the 12t. We're going to take the natural log of both sides. 20 over 3. And then we're going to be able to pull this 12t out in front. And then we can divide by everything but t on this side. So we're going to divide by 12 times the natural log of 1 plus 0.045 over 12. Same thing. And then, so putting that into our calculator, we get the natural log of 20 over 3 over the natural log of, or 12 times the natural log of 1 plus 0.045 over 12. This is approximately 42.237, and so it's going to take us roughly 42 years. So then answering with a complete sentence, it'll say, we can say it will take about 42 years.
Looking at question 29 here, the population of a rural community was 3,050 in 2010. Population increased to 3,500 in 2015. Assuming exponential growth, find the following. So we know that our equation is P of t is equal to P0 e to the kt, or maybe you're used to saying it as r, not k. That k is our rate. That's our rate. So one thing we know is that our P0 or P0 is equal to 3050 because at time is equal to 10. Or I'm sorry, at 2010, that's our initial time, that's our 0 time. So note that population at that point is 3050. So what we can do now is make the equation P of t is equal to 3050 e to the kt. But we also know what the P is whenever t is equal to 5, or 2015. So we can say 3,500 is equal to 3050 e to the k times 5. So now what we're going to do is we're going to divide both sides by 3050. So now we're going to be left with 70 over 61 is equal to e to the k 5. K times 5. So now what we want to do is get rid of that e so we can solve for k, right? So we're going to take a natural log of both sides because natural log gets rid of e's, inverse of e. So do that. E and the natural log go away. So we're left with the natural log of 70 over 61 is equal to 5k. Now to find what our rate is, we'll divide both sides by 5. And then we'll have the natural log of 70 over 61 divided by 5. That's going to give us k is equal to 0.0275, but it wants it as a percentage, so we're going to multiply by 100 to get our percentage. So our percentage is going to be 2.75%. Next, looking at part B, we're going to estimate the population in 2025. So our equation is P of t is equal to P0 e to the kt. We said that P0 was 3050, and we said K is 0.0275 times T. So now we want to know when our T is equal to 15. So we're going to do P of 15 is equal to 3050 e to the 0.0275 times 15. And then now, if we just plug it into our calculator, 3050 e to the 0.0275 times 15, we're going to have that our population after 15 years is going to be 4,607. So population will be about 4,607, should make that approximately, in the year 2025. And really what it is P15 is 4,607.298. So what we do is we round down because you can't have partial numbers of people. If it was like 0.6, we'd round up. Alright, looking at question 30 here. A sample found at a dig site was determined to have 68.78 of the C14 still remaining. Use the model Q of t is equal to Q naught e to the negative 0.000121 t. So we want to know what it is when there's 68.78% of the initial value, right? So we can say 0.6878 Q naught or Q0 is equal to e to the negative, forgot the Q0 e to the negative 0.000121 t. So both sides have a Q0, so those can go away. So So we're left with 0.6878 is equal to e to the negative 0.000121t. We want to get rid of our e, so we're going to take a natural log of both sides. That's gone, so natural log of 0.6878 is equal to negative 0.00121t. Now you want to divide both sides by that negative 0.000121. Put parentheses around that. So we know that t is going to be 3,093.035 years, and we're going to round that to the sample is about 3,093 years old.
Question 31, Part A. Determine the population of California in the year 2000. The population was given by this equation, where t is the number of years since 2000. So we can do 952 over 1 plus 1.8 e to the negative 0.018 times 0. Which is going to equal 95.2 over 1 plus, so it'll be 1.8 and then 0 times this value will be 0, so that'll be e to the 0. Simplifying it further, we get 952 over 1 plus 1.8. Anything to the 0th power is 1. So this is equal to 952 divided by 2.8, which is 34. So that means the pop in 2000 is 34 million. Let's see, predict the population of California in the year 2028. So that means our t will be 28. So 95.2 over 1 plus 1.8 e to the negative 0.018 times 28. And if we put that into our calculators, we should get 45.6 million. Part C, use the model to determine the year when the population of California would reach 68 million, round to the nearest year. So that means 68 is equal to 952 over 1 plus 1.8 e to the negative 0.018 t. And we're going to solve for t. So multiply both sides by the denominator. We'll get 68 is equal to, 68 times 1 plus 1.8 e, negative 0.018 t is equal to 95.2. At this point, I'll divide by 68 on both sides. 1 plus 1.8 e, negative 0.018 t is equal to 95.2 over 68. Subtract 1 from both sides. At this point, divide both sides by 1.8. And then take the natural log of both sides to get the t out of the exponential. And now we can divide by that negative 0.018. And after we put that in the calculator, that should equal 83.56 years, but then we were instructed to round to the nearest year, so that will be 84 years. What is the limiting value of the population of California under this model? That'll be whatever's in the numerator. In this case, it'll be 95.2 million, and we get that from the numerator. All right, 32, the table gives diameter in millimeters of a sugar maple tree along the corresponding age in years for 6 different trees. State which model best represents the data using the graphing capabilities of your calculator. So using that will be in stat, calc, and the first one that they ask is for linear. If we look at the linear r or r squared value, that r squared value is equal to 0.657. The exponential we have in r squared equal to 0.426, and the logarithmic. We have an r squared equal to 0.999. So the best model is the logarithmic. Other ways of doing that would be looking, getting a scatter plot and seeing what it generally does. Or the other one would be looking at the different r squared values of your calculator. Part B, using it, find it. So that's where you put those in the list. If you've done it the way that I've been showing you, or that I've done it here, you'll already have those values where it will be y equals 3.33 plus 14.93 natural log of x. From that model, from part B, the best fits the data to determine the age of a sugar maple tree that has a diameter of 150 millimeters, round to the nearest year, show all your work. Do y equals 3.33 plus 14.93 natural log of 150. We put that into our calculator and we get 78.14, but then we were asked to round to the nearest year, which will be 78 years. All right, is the ordered pair 3, -4 a solution to the following system of equations? So we plug in the ordered pair into both equations and see if they hold. So 7, 3 for the x, plus 5 times -4 for the y is equal to 1. 21 minus 20 is equal to 1. 1 equals 1. So it holds for the first equation. We'll see if it holds for the second equation. -6 times 3 minus 8 times -4 is equal to 14. -18 plus 32 equals 14, and indeed 14 equals 14. So yes.